Okay, well, let's look at a brief summary of the problem that we just did. For this example, the general population of men leaves an average of 15.8% tip with a standard deviation of 2.4 when a waitress wore a white shirt, which was sort of the default. Therefore, the hypotheses were that I'm speculating about the mean tipping percentage when they wore a red shirt. And if I assume it has no effect, then that will be the same as the white shirt, which is sort of the default. On the other hand, if I'm saying it does have an effect to wear a red shirt, I'm saying it'll make a difference. That tipping percentage will be either less or more, but not equal to generally. Now, again, that's a little inauthentic. Usually we have an idea of which direction it'll make it change, but just for the sake of introducing the subject, we start off with a two-tailed test. We located a critical region. In this case, at alpha of 0.5, we went to the tables and found it was 1.96 would put 2.5% in each tail. It's not always that clean. We got lucky on that one example that it was so clean. We compute the test statistic, which is basically Z obtained. And with these parameters, as we'll walk through, once I know the standard deviation and the size of the sample, I can compute the standard error, which will allow me to obtain to calculate that value of Z obtained. And here's what we found. The Z-score was in the critical region, which means that this sample is very unlikely if the null hypothesis is true. Therefore, we reject the null hypothesis, conclude that wearing a red shirt did have an effect on men's tipping. Now, is it possible that we made an error here? Is it possible, essentially, that mean was 16.7 by chance, and it has nothing to do with the red shirt? Yes. And we'll get to that later, but if that were the case, it's an unavoidable occasional error known as a type 1 error when we rejected a null hypothesis that was produced largely by chance. The result is said to be significant or statistically significant if it's very unlikely to occur when the null hypothesis is true. And in this case, a sample mean is very unlikely to occur when the null hypothesis is true. Now, that is, the result is sufficient to reject the null. So we throw this term around. What we want is the null to be rejected, and we want statistical significance. So this is something that we have to live with in the social sciences. It's the case that in other disciplines, they have the luxury of a proof. I'll never forget, I went to grad school with a guy that was in the math department, and he was on his way to defend his dissertation. And I said, hey, well, you nervous? And he goes, nope, I've proved it. And his dissertation was an irrefutable, incontrovertible proof of something to do with prime numbers. I don't remember it, of course. But I wish we had that in the social sciences. In the social sciences, we have an apparent effect that frankly could have appeared by chance. And therefore, we're left to say things like statistically significance. And of course, we also quote effect sizes we'll talk about later. Can we take a contrary example? Yes. And I think I might want to get to this in the next clip, where we failed to reject the null hypothesis. Yes. If we had gotten a sample mean that was lower than 16.7, we would have failed to reject the null hypothesis potentially. And we'll take a look at that here in a second.